Hi, everyone. My name is Chris Miller, and I'm the CEO and founder of Cloud Brigade. We're a technical consultancy and an AWS partner. Now, technical consultancy is a broad term, and as an AWS partner, we get to touch a lot of different services. I'm a technical founder, a machine learning hero, and I like to think of myself as a geek with social skills. This picture of me is in a 1942 Stearman biplane that I got to fly. And so there's no surprise I have a smile on my face. It was the first time ever flying an airplane. And as you might imagine, I love to take new challenges. I want to talk about our agenda today so you know what to expect. And we're going to learn how we are building a machine learning and Internet of Things solution on AWS. Smart city is a term used to describe AI solutions that solve age-old problems. And our smart city solution is designed to ease traffic congestion. Today, we'll talk about the components of a solution like this. We'll talk about new ways to collect traffic data, using machine learning models for decision making, leveraging Internet of Things devices, and networking all these pieces together. Every solution to a problem usually has a good story behind it, and this is mine. I live in a small beach town called Santa Cruz in California. There's not a lot of miles of roads, but it's a tourist destination. We have a beautiful boardwalk and lots of things to do and nice weather. So as a result, we get a lot of traffic, and it makes it really difficult to get around. Just traveling 4 miles from my house to my office can take 30 minutes. That's just crazy. So one of these days, I was stuck in traffic and I started wondering, can AI and machine learning be used to improve this situation, to reduce the traffic congestion? Software development is often at the center of our work. And several years before, I realized we needed to embrace machine learning or we were going to be left behind by the competition. So my machine learning journey was a very interesting one. You see, I had recently won a car race, and probably not the kind of car race you're thinking of. I won the AWS Deep Racer event at the 2019 Santa Clara Summit. AWS Deep Racer is a small self-driving model car which serves as a kind of toolkit and learning tool for developers to learn machine learning. From that experience, I had a hunch that reinforcement learning might be a useful way to train a machine learning model and to improve traffic throughput. I did some digging on the internet, and I actually found some academic papers on the subject, and this really planted the seed for what was about to come. Have you ever sat at a traffic light and noticed a big metal box on the sidewalk and wondered what's inside it? Inside this box is a bunch of old electronics suitable for a museum exhibit. This stuff is literally 30 years old. They use something called programmable logic controllers, and they're rudimentary and dependable, but their logic capability is really quite limited. There's no sense of queuing, and the boxes pretty much operate as a standalone unit without talking to the box down the street. The way they operate is they sense a car at the light and they turn the light green for a preset period of time, like 20 seconds. And they often do this badly. Like you've probably been stuck at a light for a long period of time and wondering, hey, there's no cars around. Like, why isn't the light turning green? This just speaks to the limitation of these old tried and true systems that they're just old. Fortunately, we have new technology to replace this. Let's talk about the data problem, because that's a big component of what's going on here. Have you noticed a group of rectangles or circles in the street at every stoplight? In this picture, you can see a circle, and they had cut a slot in the street and then filled it with tar. And actually, there's a wire loop inside of that slot, and it's known as a ground loop sensor. They use something called the Hall effect, which detects a magnetic field generated when a large metal object is on top of the loop. So when a car or a truck or a bus pulls on top of this loop, it sends a tiny little electrical voltage to the programmable logic controller and tells it, hey, there's a car here. You're going to need to do your routine of turning the light green. Have you ever wondered how an electric guitar pickup works? It's the same kind of principle. There's a coil there, and as the strings vibrate over that coil, it detects that electrical voltage and then sends that to the amplifier and plays the sounds that we all like to hear. The problem with this type of sensor is it can only detect one car at a stoplight. So if there are 2 cars or 10 cars, it just has no idea. It's just not designed for this. These systems are also not designed to measure traffic volumes. To know which direction traffic is going once the cars enter the intersection, like going left or going right. And they don't have any knowledge of what traffic is about to arrive from the preceding intersection. So the result of this is just really inefficient queuing of cars based on simple timers. So, what does a modern solution to a 100-year-old problem look like? A smart traffic solution is designed to use modern technology advancements to do a better job. And it's only recently that we've really had the ability to apply AI technology to these types of problems. Now we have things like computer vision, which can be used to gather more data than these simple sensors. We have machine learning, which we can train to make better decisions. We have Internet of Things devices, which can execute those decisions. And we have advanced communication networks to tie it all together. The technology has matured and these systems really work well together. In order to design and build such a complex system with so many variables, you really need a good plan. A good plan starts with setting some goals. So we looked at the problem and we determined that we knew we needed to collect better data, which we can do with the cameras. We knew that we wanted to use deep learning, which is a very capable tool for this. And of course, we want to see an improvement, or there's really no point in going down this road. Pun intended, of course. Perhaps one of the more challenging goals is finding a way to measure the results. As they say, if you can't measure it, you can't manage it. An easy way to measure improvement is increased throughput, right? If you can get more cars down the street, that's a plus. Problem is you can't magically reduce congestion by increasing throughput alone. It's not just the throughput on the main highway that you want. If that were the case, you could just orphan all the cars on the side streets and let them stack up, and you'd end up with a lot of angry people. Obviously, that isn't a solution. We needed a better way to simulate the results of a lot of very complex routing decisions. Whenever you consider using machine learning to solve a problem, you first need to consider, is this problem a machine learning problem? Can machine learning potentially do a better job than those ground loops and those PLCs? Can we get the type and volume of data that we need to make better decisions? What kind of tools, such as hardware and software, might we need to build this solution? How can we make all of those components talk to each other in real time? And finally, what does success look like? For us, success looks like a 10% reduction in traffic congestion. Think about the benefits. How many hours are people sitting in cars? Can we give back time to people that they can spend more meaningfully with their friends and family? How many tons of CO2 can we keep out of the atmosphere generated from cars idling at stoplights and acceleration cycles where you get on the gas and the next light turns red and the next light turns red and you wonder, why can't I just have green lights all the way? What other benefits can we achieve? Let's look at how we can solve the data problem. In order for us to build a data-driven traffic system, we had to think hard about what data we needed to collect to make better decisions. We considered how we would use computer vision to collect the data, and then we worked the problem back from there. Computer vision brings a lot to the table. It gives us the ability not only to detect and classify vehicles, but also to determine their direction and speed. Now, you're probably wondering, why would we care what kind of vehicle is at the stoplight? Well, one example is that different types of vehicles have different acceleration and deceleration profiles. This impacts the amount of time it would take for a vehicle to get from one traffic light to another. So, while your sports car is more likely to make it to the next light fast, that's certainly not going to be the case if you're stuck behind a semi-truck. What if you wanted to give preferential treatment to certain kinds of vehicles, like a city bus, or a fire engine, or a police car? Objects classification gives us an enriched data set for us to make these kinds of complex decisions. Lastly, we talked about how ground loops can't measure queue length. With computer vision, we now have this ability because we can see down the street and get a sense of how many cars are queued up in each direction at a light. As you can see, we're collecting a lot of complex data, and we have a lot of complex decisions to make based on all of that data. A simple rules-based approach isn't going to cut it. That's exactly what the PLCs do and is very limited. Fortunately, deep learning is a perfect type of solution to process this data and to build an intelligent model to make these kinds of decisions. Deep learning provides a multi-layer neural network which allows us to train a reinforcement learning model, one that considers all of the possible combinations of variables. We are talking about millions of scenarios here, not just one intersection, but across miles of roadway in tens or hundreds of intersections. Reinforcement learning uses a concept known as explore-exploit as an efficient way to navigate through plausible scenarios without wasting a bunch of time on every single scenario. This is exactly how AWS Deep Racer learns to drive, exploring the environment to acquire knowledge, and then exploiting this learned knowledge to make the optimal decisions with the highest possible outcome. Epsilon greedy is the most common and simplest algorithm for balancing the trade-off between exploring and exploiting by choosing them randomly. In order to simulate all of these complex decisions, we use something called Sumo. It's a really great open source tool used by planners to plan urban mobility. And Sumo does a lot of things, but one thing it was particularly attractive about this was being able to run simulations in real time based on real or synthetically generated traffic data. It does this using a client-server architecture, which made it perfect for connecting to a machine learning model that was hosted in AWS. Now that we've talked about the components of our smart traffic solution, let's talk about the process for building the machine learning model. First, we need data to train the model. In a perfect world, that would be real-world data. But since that in itself requires a complex solution involving computer vision, we decided to generate synthetic data. I'll talk about that in a minute. In this way, we were able to code for our smart traffic solution without being bottlenecked by executing the project in a linear fashion. That is to say, we could focus on the hardest part of the project, which is building the machine learning algorithm, without getting tripped up by building an exotic computer vision solution. Next, we train the machine learning model, and we record the results, such as the rewards given over time and the distribution of action predictions. And then we tune the model by making changes to the hyperparameters. Next, we evaluate the training of the model and determine if the recorded metrics show that the model is in fact learning. We can do this through visualizations of the previously recorded metrics. After evaluation, we deploy our machine learning model on an endpoint so we can begin testing the model. So this is the exciting part. We test our model by sending test data to the endpoint for inferencing. Then we take that result and we feed it back to Sumo. As you might imagine, we can't simply evaluate our model by looking at graphs in a Jupyter notebook. That's not going to give us the big picture view that we need. There's a subjective nature to the evaluation where you simply need to see where the cars are going, where are they stacking up, when are the lights turning green. You just need to be able to see that larger world of what's going on. Based on this evaluation and simulation process, we continue refining the model until it performs as we expect. This doesn't just end once you have a working model. You may also need to retrain your model continuously using new data from the real world. So the model will adapt to changes in traffic patterns over time, learn from seasonal changes, the weather, holidays, anything that might make one day different than another. It's fascinating, really, the number of variables that can be considered here. So, I know you've been wondering how one would synthetically generate traffic data. Well, this is where Sumo comes to the rescue. Sumo comes with a feature known as Tracey, or the Traffic Control Interface. We are able to define a virtual world within Sumo and then ask Tracey to examine that world and generate traffic based on certain rules we give it. Taking advantage of the client-server architecture, we are able to generate traffic data on the fly, feed it to our machine learning model's endpoint, and then display the result of the decision in Sumo. When I say decision, I mean you can see the model decide when to turn the lights red and to turn them green based on the input data. Now, I know you're all wanting to know more about the deep learning model and how it works. If you're new to ML, I highly recommend checking out AWS DeepRacer. DeepRacer makes it easy to get familiar with these concepts in an approachable way and explore the data science concepts through experimentation. Remember, DeepRacer was the beginning of my machine learning journey. We chose to use the RL Coach Toolkit, RL for Reinforcement Learning, from Intel. It's used in DeepRacer, and it's also integrated into Amazon SageMaker. The RL Coach Toolkit provides a Python framework with all of the tools you need to build a variety of reinforcement learning models. We also used OpenAI. They provide an environment which integrates with RL Coach. Lastly, we used the DeepQ network agent. We initially experimented with something called the Proximal Policy Optimization Agent, or PPO, but the action space was too limited, and we found it didn't work with really complex networks. We just simply outgrew it. Let's look at the architecture of how you would build a solution like this in AWS. We talked about using a camera to collect the data, but the camera has to be able to communicate with our model. In our case, the camera is deployed as an Internet of Things device, and it can leverage something called MQTT, or the Mosquito Protocol, to send data in lightweight JSON packets. Another thing I would say about this is that the IoT devices don't have to be connected to Wi-Fi. They can take advantage of cellular networks, and because the data is fairly lightweight, you're not going to get bottlenecked by load bandwidth on things like cellular connections. Although, obviously, new standards are coming out with a lot more bandwidth available. We use AWS IoT Core to manage the data streams. Likewise, we use IoT Core to manage other functions that ultimately control the traffic signal, such as an IoT device that would be a companion inside of that metal box, or hopefully even eliminate it to control those lights. To act upon and manage these data streams, we use AWS Lambda for serverless code execution and getting the data to where it needs to go in a secure way. Lambda can handle routing our real-time traffic data to our machine learning endpoint, route the decision back to the traffic light controller, as well as store that data for model retraining and analytics. With such a complex system, you can't just leave it on autopilot. You will need to go in and make sure that it's operating properly, and a good analytics dashboard can help you to do that. With the data in S3, we also have the option of consuming the data for other uses in the future inside of our platform. So let's dig a little bit deeper into this reference diagram for this solution. So for the camera, there are a variety of options that can be used, from Raspberry Pis or Jetson Nano to products that are available through AWS, such as Panorama. In this case, you would deploy your code to your IoT camera. You can use AWS IoT Greengrass to push that code down and to manage that device. And again, the camera can communicate efficiently with small JSON packets that are communicated using something called the pub/sub mechanism within the MQTT protocol. So these packets end up in AWS IoT Core, and then they can be sent to a Lambda function and then forwarded on to a machine learning endpoint, such as one that's hosted in AWS SageMaker. So once the decision is returned from the machine learning model, it's sent back to AWS Lambda, and we can look at the decision. We can do any kind of post-processing of that decision, any other kind of data collection, and then we can send a JSON packet back to AWS IoT Core, where it will then relay that to the controller using the MQTT protocol. For the controllers, you can use everything from an Arduino to a Raspberry Pi to other kinds of small, inexpensive industrial computing solutions. And all the tools and code are available there to load on to take advantage of things like AWS IoT Greengrass and the Mosquito protocol. And everything's SSL encrypted, so it's nice and secure. So as I said, AWS Lambda, as it is receiving this data, we can pump that into files into S3, which is easily consumable by a solution like Amazon QuickSight. And training pipelines can then consume that data and then retrain our model, as I previously mentioned, where the traffic patterns change due to holidays or weather conditions or so forth. So I know this is the moment you've all been waiting for. You get to see our smart traffic solution in action. So what we're looking at here on the left is the Sumo window. This is a Java application that runs on any type of desktop. And Tracy is generating the synthetic data and feeding that to Sumo, and also feeding that to our machine learning endpoint in the cloud. In the right pane, you can see our code in action, receiving the inferences from the machine learning endpoint, and then feeding it back to Sumo. And if you look real closely in the intersections, you can see small green and red lines, and you can see how the cars are interacting with the stoplights. And it's doing a pretty good job. Obviously, this is sped up very fast, but we're not seeing any traffic jams here. Now, I know we've covered a lot today, and you're probably interested in what other uses of AI and machine learning are available. So we put together a list of additional resources. The first one is a smart garage door opener that uses AWS Deep Lens and Amazon Rekognition. If you didn't know, AWS Deep Lens is a companion device to AWS Deep Racer. It uses a similar kind of camera and computer, and it allows developers to build computer vision solutions in a really easy way that's integrated with AWS. For larger solutions, you can use AWS Panorama, which is a device that allows you to connect existing IP cameras. And the Panorama device it's kind of like a Deep Lens on steroids. So you're able to run multiple machine learning workloads on the Panorama device. So the third, we have a shelf monitoring solution that also uses AWS Panorama. And finally, if you want to learn more about the beginnings of our project, you can look at our smart traffic using machine learning. Lastly, I would love to give a shout out to Matt Patterson, our data scientist, who made big contributions to this project. Thank you very much for watching our presentation.